Thank you very much. It's a real pleasure to speak in honor of Jean-Michel. So I've gotten a lot of inspiration from you over the years, and thank you very much. This headset makes me feel like it should break out in song or something, but I won't. Don't worry, I won't. Okay, so what I want to talk about today are three sort of short pieces. So I decided to do this rather than talk about one thing in sort of great depth, because the two first things are, for the most part, older work, and I wanted to sort of try to focus on some common themes to a number of different things, where I'm interested in spatial asymptotics of various canonical metrics and different ways that one derives them, and that how they can be sort of used in somewhat surprising ways. So I think asymptotic expansions are at the core of a lot of what Jean-Michel does, so I thought this was an appropriate topic. So I'll be talking about three separate areas. Obviously, since I'm talking about a number of things, I won't go into enormous detail on any one of them. The first is some work that's very closely related to what Simon Donaldson was talking about the other day. Part of the large push in understanding the Kähler-Einstein program on Fano manifolds involved what are called Kähler-Einstein edge metrics, we call cone metrics. And so there have been a couple of different ways of thinking about these, and so one approach which I was involved in a few years ago turned out to be very successful, and there was a way in which asymptotic expansions, so what was a priori just a regularity theorem for solution of a Monge-Ampere equation, turned out to play a very crucial role in an unexpected way, and I wanted to explain that a little bit. The second thing is, let me see, here we go. The second thing is another rather different classical topic, so a very classical thing, the Riemann moduli space of genus gamma surfaces, and in particular the Weil-Petersson metric on it. And something that I got involved in with a few people, so Werner Müller and Li Zhengji and Andras Fasci, we were trying to understand what seems like a bit of an odd problem, which is to look at the Laplacian on moduli space, so with respect to the Weil-Petersson metric. So it's a rather singular object, this metric. I mean, there's some rather severe metric singularities, and we were interested in understanding some basic properties, which we did, and then it led me to some problems of understanding the Weil-Petersson metric better, and I was rather surprised to find that certainly when I talked to some of the experts, like Scott Wolpert, he didn't know the properties I was asking, and so we had to go back and extend some of the known theory of the Weil-Petersson metric to understand a sort of higher asymptotics at the divisors. And the last is a subject which has received a lot of airplay in the ADS-CFT correspondence, Poincare-Einstein metrics, and the study of the renormalized volume. So we'll see how I do on time. I'll certainly talk about the first two. I may not get to the third. So let me remind you a little bit about the whole story of Kähler-Einstein metrics. So a Monge-Ampere equation, complex Monge-Ampere equation looks roughly like the following. So I have a determinant of the identity plus the complex Hessian is some function involving the first and up to the first derivatives of the function phi. And because of the geometric origin, I'd like to say that the matrix in the parentheses there is a positive definite, so that this is an elliptic problem. It's a fully nonlinear elliptic problem. Of course, this can be formulated intrinsically, and from the geometric point of view, if G is Kähler and if phi is a real valued function, then we get a new Kähler metric, which is defined by taking G plus root minus 1 times the complex Hessian. And we look at the set of all such metrics so that the set of all such metrics obtained in this way. So G itself has a Ricci tensor, which we turn into a Ricci form, and we have the well-known relationship that the cohomology class of the Ricci form divided by 2 pi I is the first Chern class, and the standard problem is to realize if C1 of M is it's definite or 0, can one find a metric which is Kähler-Einstein? So the point being that this condition, so in order for, so I didn't, well, there I wrote down the Kähler-Einstein condition. So I want the Ricci form to be a constant multiple of the Kähler form, omega sub G. And if that's possible, then that requires that C1 of M be definite, or if mu is equal to 0, that C1 of M be the 0 class. And so this happens, well, in the cases there. And so this is now completely understood. So C1 of M negative and 0 were, of course, the famous theorems in the 70s of Aubin and St. Yao. And just this last year, there was this dramatic existence result in the Fano case by Tian and Chen Donaldson and Son. So the way that one goes about any of these problems is to solve this complex Monge-Ampere equation. So this equation is this ratio of these two determinants written in a local coordinate system. So this has a invariant meaning independent of coordinates, is equal to e to some function. It's a smooth function that depends on the initial metric, and it measures in some sense how far that missed being Kähler-Einstein itself, minus mu times phi. Mu is exactly the constant, the Einstein constant. Okay, so this is the equation that one has to solve. And again, assuming that G plus phi ij is positive definite, this is fully nonlinear elliptic. Okay, so the variant of this problem, so that's the smooth case, a very quick review of sort of a very well-known story. What I want to be emphasizing today is a rather different, though obviously closely related story that emerged in a couple of different venues, which I'll remind you of. So one starts again with a compact Kähler manifold, but you are looking for invariance of pairs, so a manifold and its divisor, and some divisor inside of it. So in particular, we'll take a divisor which is either, well, in the simpler cases, it's just a single smooth submanifold, complex codimension 1, or it can be a union of these which cross. So the picture you should have in mind is sort of divisors that cross like this. Maybe there's many ones of these, but they satisfy technical condition of being simple normal crossing, so it's essentially a transversality type condition. And so in particular, what this simple normal crossing means is that each di can be described as, so I can choose local coordinates z1 through zn, so each di is the zero set of one of those coordinates zi, and the intersections are described by some subset of these zi's vanishing. Okay, so this is what simple normal crossings means in local coordinates. So the problem itself was posed by Tian in the early 1990s, and his motivation was really in the negative case. So he was interested in the case where mu is negative, and he was interested in certain applications of Kähler-Einstein metrics in the negative or zero case, which were in particular this famous Maioka-Yau inequality. So if you had a Kähler-Einstein metric, then you could prove a certain inequality on the Turing classes, which I didn't write down here, unfortunately. And the hope was to extend that to a slightly broader class of manifolds. And so what one does is, so I will draw the picture here. So let's suppose that we just have a single divisor. What one's looking for are exactly the objects that we've heard about a couple of times already this week, which are metrics with cones in each of the cross sections. So here's the divisor D. This is, let's say one component of D. And transversely to D, I have cones, so it really looks like a bundle of two-dimensional cones over D, and this is what I call an edge rather than a cone. So this appeared in Atiya's talk and Donaldson's talk. So it turns out that there's a funny cohomological condition which is going to replace the Kähler-Einstein condition that we saw a few slides back. So instead of saying that C1 of M looked like a fixed multiple of the Kähler class, one actually allows to perturb by scalar multiples of C1 of the line bundles corresponding to these divisors. So in other words, what one's doing is you're allowing a little bit of extra flexibility in the cohomological condition, and you're hoping that that allows you to get a slightly richer existence theory. So in other words, if you impose this cohomological condition, and I'll show you the geometric implication of that in just a moment, then you want to ask for a Kähler-Einstein metric which has Ricci form given by, well, just that multiple, mu times the Kähler form. But these extra parameters, these betas here, correspond to exactly the geometry along the divisor. Namely, this corresponds to the cone angle in the transverse direction. Okay, so the cone angle is supposed to be 2 pi beta j along dj. So in particular, the limiting case beta j is equal to 1 corresponds to standard smooth the problem, and of course then the cohomological condition is collapsed to the standard one. And beta j is equal to 0 corresponds to something that was studied in the 80s by Tian and Yao, which was looking for complete metrics. So the cone angle going to 0, and again, this is a geometric situation we've seen a couple times before this week. The cone angle going to 0 means in some sense it's developing some kind of a cusp or a cylindrical end. Okay, so those are the two limiting situations, and these families of cone metrics are interpolating in between, let's say, things that roughly speaking have cylindrical geometry, well, not quite, and on the other hand, smooth metrics. Okay, so there's an analogous situation I just wanted to very briefly remind you of, which was proposed by Thurston in the 70s as a route to geometrization, or at least of a particular case in geometrization, which was to take finite volume hyperbolic three-manifolds and to try to close them up. So at infinity, the cross-section looks like a 2 torus. Okay, so if I take a finite volume hyperbolic three-manifold, then there's some sort of cusp out here, and the cross-section is a 2 torus, or maybe a finite quotient of a 2 torus. So one can try to turn this into a compact object by closing the cusp, and that requires a choice, and you make a choice of Dane surgery. And it's a fairly easy perturbation argument to close it up to a compact object which has an edge along the 2 torus. Okay, so in fact, excuse me, there's along the central core of the 2 torus, so you have a what's called he called a cone manifold or a conifold. So you have a hyperbolic structure, and it collapses to forming an edge with angle 2 pi beta, where in this case beta is very small if you've sort of closed it off very near infinity. Okay, so this was an old proposal, and then Thurston's idea was to look at these hyperbolic cone manifolds and to try to deform this picture, maintaining the hyperbolic structure and letting beta get larger and larger and hopefully converging all the way to 1 so that you get a smooth hyperbolic metric. Okay? So this, in fact, has now been understood, though obviously wasn't the route to proving geometrization, but we now understand pretty well exactly how this deformation theory works. And there's a lot of interesting surprises here, which are very analogous to what happens in this complex Kähler-Einstein situation I'm talking about, that there's a very good deformation theory that sort of starts breaking down as you get closer and closer to the smooth case. So as the cone angle gets closer to 2 pi, then you lose a compactness, possibly, for certain geometries, and that's what's very subtle to understand, is, you know, there's certain cases where it's known there's no smooth hyperbolic structure, and so something has to go wrong in this deformation process. Okay, and that's, like I say, that is understood. Okay, so let me go back to this Kähler-Einstein edge problem. So the problem of understanding, so this, namely, can one find a Kähler-Einstein metric that has these specified cone angles, provided you assume this cohomological condition. So this has now been fully resolved in the past couple of years in a couple of papers. And there are two sort of rather different cases. The first when D is smooth, and the second when D has several components. And I'll say a few words about both of these. Now, the Tian-Donaldson conjecture, so I didn't say this a few times back, so I had pointed out that Tian had proposed a use for these in the early 90s. Donaldson had proposed a rather different sort of use several years ago, which was to find a solution of this slightly more flexible problem, and then to try to do exactly the same thing as Thurston had proposed, but in this complex setting, namely to try to take families of Kähler-Einstein metrics with edges and to try to push them to being smooth. Right? And that's eventually what this big theorem was this last year. I mean, understanding this Kähler-Einstein case in a smooth Fano case and relating that to case stability. So it was somehow centered around that idea. Okay? So the thing that we were able to understand was the full existence theory for these Kähler-Einstein edge metrics with any specified cone angle beta less than 1. Okay? So there was a lot of previous work on this. The problem had been around for some time, and I'd been thinking about this with Alia Jeffers quite some time ago, 10 or 15 years ago. And in the past 2 or 3 years, because of Donaldson's interest in this and its applications, there were a huge host of papers. And it turns out that all of these papers had a particular defect in that either they were working with special Ds, or they worked with cone angles less than or equal to 1/2, and both of those are sort of simpler for one reason or another. So it turns out that, and for reasons I'll be explaining, when beta is less than or equal to 1/2, then it turns out that much of the classical approaches still works. I mean, they're all very interesting aspects of all of these papers, but they don't provide as much information as one would ideally like. So we were hoping for sort of a sharper theorem that works in the general complicated simple normal crossing divisor case and gives you very sharp asymptotics. So that was our goal. As I just pointed out, what's sometimes called the orbifold regime, because if you take a finite quotient of a Kähler manifold with fixed point set of divisor, then you'll wind up with one of these edge metrics where the cone angle is 2 pi over k, where k is the covering number, and that's always corresponds to cone angle, well, with angle less than or equal to pi, which is beta less than or equal to 1/2. And it turns out there's some remarkably different things that crop up in the analysis when beta is greater than 1/2. So it turns out that it's sort of a whole different story when beta is less than 1/2 and beta is greater than 1/2. And I'll try to say a few words about that. Okay, so one would like to approach this by the same old continuity method, which is to deform the complex Monge-Ampere equation by putting this parameter t in front of the inhomogeneous term. When t is equal to 0, one knows the solution, namely phi is equal to 0, then you try to prove openness and closedness in the usual way. So this was the Aubin-Yau method that was very successful, and to prove openness in the smooth compact case, so to show that J is open, you apply the implicit function theorem, in fact, the inverse function theorem. You just take the linearization of this equation. It's essentially the Laplacian for the metric G sub phi, and one has good Schauder estimates for that on a closed manifold, and that allows you to get the openness just by applying the implicit function theorem. And the closedness was, of course, the hard work. This was proving the a priori estimates, and just to remind you, because we're going to come to them in a few moments, one has to prove a priori estimates on the C0 norm, the sup norm of phi, the C2 norm, and the C3 norm of phi. So you need tower of such estimates. The C0 estimate is sort of the fundamental one, saying that the solution stays bounded. C2 estimate depends on that, and the C3 or the C2 alpha estimate depends on the C2 bound. And they're all computationally rather difficult and justly very famous. Okay, so we want to follow the same strategy in this Kähler-Einstein edge case. And so what this will involve is to first write down a model metric. Now, I haven't explained to you where the cohomological condition that I described several slides back comes in. So here's the flat model. So this is a metric that has exactly the right geometry if you were in CN and the divisors were just the standard coordinate hyperplanes. Okay, so there it is, and this is sort of the conformal form. It's written in this form which looks, well, I mean, there's a singular factor. I mean, the betas are less than 1, so that blows up, but it's not blowing up fast enough to be complete. And if you do a simple change of variables, you'll see that the metric corresponding to this Kähler form actually has exactly the right cone angle. Okay? And because of the simple normal crossing, these different factors are just independent of one another. These cones are just happening in different directions. And then on the intersection of all the divisors, you just have the standard flat metric. Okay, well, if you want to replicate that geometrically, you want to take the Kähler form corresponding to a fixed background smooth metric, and you want to perturb it by something that mimics this type of behavior. And what you have to work with if you have a bunch of divisors are sections, holomorphic sections, which define those divisors, so sections of the corresponding line bundles. So you call those sections Sj, and you just take their norm to the power 2 beta j dd bar of those, and that's what you add on. Okay? Now, it turns out that the positivity of this object, so you can certainly write this down for any collection of divisors, but the positivity of this form here, so that it gives you a metric, is exactly what corresponds to that cohomological condition. So that's where it comes in. Okay? So that's why it's a necessary condition. And anyway, so you've written down this metric, and you'd like to know if you start with that as your initial guess, which is not going to be Kähler-Einstein unless you were extremely lucky, how can you start perturbing it? So we're going to follow the same type of continuity argument, and it turns out that both the openness and the closedness are turn out to be completely different than in the smooth case. So I'm not going to say too much about the openness argument in this talk. So again, the linearization at any point t naught along the path would be the Laplacian plus a constant. And the non-standard aspect of this is that this is an operator on this singular space. I'll write down what the Laplacian looks like on these spaces momentarily. But it's a degenerate operator that's sort of cone-like in certain variables, and one needs to invoke or prove a number of linear estimates for that. And fortunately, there's a very comprehensive theory which does that. But even within that sort of now somewhat old theory, it turns out that one asks for rather non-standard properties of the mapping. So I don't want to get into that in this talk, but that's sort of an interesting part. For the closedness argument, it turns out that if one tries to follow the Mazzeo approach, their C2 estimate relies on lower bounds of the bisectional curvature. So this is the bisectional curvature on two planes which are pairs of vectors which are preserved by J. And so, right, so I mean, it doesn't really matter if you're on a compact smooth manifold that, it requires bounds on the bisectional curvature, but if you actually look closely, it requires lower bounds rather than upper bounds. And here's exactly the problem that we face when the cone angles are bigger than pi. Okay, so this is sort of the huge change in geometry, is that all of a sudden, this initial model metric that I wrote down, its curvatures are unbounded. They're unbounded below the bisectional curvatures. So that's a computation, and it turns out, this is something that we worried about for quite some time, it turns out that there's actually obstructions. There's just no way to find a good initial metric for which the bisectional curvatures are not going to be unbounded below. So this means that this continuity method just seems to fail. Now, we adopted a method that my collaborator Yanir Rubinstein had initially used in his thesis. He'd worked on something called the Kähler-Ricci iteration, which is essentially a discretized Kähler-Ricci flow. And he'd instead put the parameter, instead of trying to deform away the f, he'd put the parameter in front of the phi variable there. Okay, so it's just a different continuity path. And you study this when s ranges from minus infinity up to mu. So mu is the Einstein constant you're trying to get. And you deform along this entire path. It turns out that if you find a solution for s very negative, well, you can do that by perturbative methods. It's a slightly degenerate problem, so you have to do some work, but that's possible. This is very closely related to something that Damon Wu had done about 10 years ago. But the big advantage of this continuity method is that if I look at the metric defined by g sub phi, at any point s along the path, just by definition, its Ricci curvature is bounded below. So in some sense, the fact that I have a solution of this exact equation is going to tell me that the solution for a given value of s has Ricci curvature bounded below by s. Okay, and that turns out to be enormously useful. Okay, so let me just talk about where the asymptotics come in, which, as I promised, was going to be the theme of the talk. So let's just look at the smooth divisor case. So here, the metric looks like, and excuse me, I believe there's a misprint here. This should be a 2 beta minus 2, forgive me. So that's this singular factor. One looks at a change of coordinates, and I'm not sure if I said this on the next slide, but what this cone metric is supposed to look like in polar coordinates is dr squared plus beta squared r squared d theta squared. So that's where the cone angle arises. And you can get to that from this sort of different looking ansatz by a change of variables. So by this change of variables here. Okay, and in these coordinates, this is what the Laplacian looks like. So it looks like the Laplacian in a two-dimensional cone plus the Laplacian on the cross-section, on the divisor. Of course, I'm omitting all the cross terms and higher order terms. There's no cross terms at leading order part. That's very important here. And there's no sort of great advantage to writing out what all the junk terms look like, but one obviously has to deal with them. So this is just a simulacrum of what the actual operator looks like. And so one needs to find function spaces in which this has good mapping and regularity properties. And so there were two choices here. so what I call the wedge spaces and the edge spaces. And they look a bit weird, but if you think geometrically, you'd say, well, I'd like to define Holder spaces, or just define CK spaces. I mean, just K times differentiable spaces by differentiating with respect to the vector fields that constitute this operator. So d by dr, 1 over r d by d theta, and d by dy. So that's exactly the vector fields that appear here. Okay? Those are on the edge itself, those are the vector fields of bounded length. Those are the unit length vector fields, or approximate unit length vector fields. And this was in the approach that Donaldson had been proposing and carried out in existence theory by Brendel when beta was less than 1/2. These, you get away with using these vector fields. Now you take a very small change to this, which is just you multiply each of these guys by r, and you wind up with different looking function spaces. So if you think about what the big difference is, well, suppose you have something that's 5 times differentiable with respect to these vector fields or with respect to these vector fields. What more or less do you know if it's, in those two spaces? And the answer is simply that, you're differentiating with respect to rdr and rdy. So, if you're 5 times differentiable, you have full regularity in theta, right? But the fact that you're differentiating with respect to rdr means that you're allowed to have funny exponents. I could easily have, an r to some non-integer power, some r to a gamma. Every time I hit that with rdr, it doesn't get worse. It doesn't get better, but it doesn't get worse. Whereas if I differentiate that with respect to d by dr, it lowers by 1, and I immediately, the minute I've differentiated more than gamma times, I become singular. Okay? So, carrying on with our approach here, what we did was we mimicked what sort of a very standard construction in the in L2 theory, which is you look at the Friedrichs domain, but adapted to these Holder spaces. So W or E means with respect to either of these two choices of vector fields. Okay, so namely, I'm just looking at functions which are twice differentiable or 2 plus alpha times differentiable in either of these senses. So I have to choose one and stick with it, whose Laplacian is k times differentiable. So I call that the dk alpha wedge or edge Holder Friedrichs domain. So the thing to be aware of here is that the Laplacian has d by drs, but not r d by drs in it. So that means that if I had something in the edge space, so remember that I'm differentiating with respect to, I'm allowing myself, to say that I'm in C2 alpha edge means, u rdr of u and rdr squared of u is okay. If I differentiate with respect to d by dr squared, it could blow up. It could blow up like r to the minus 2. So if I just, it seems like these edge spaces are inappropriate because the Laplacian is not very well behaved on them. Okay, if I take something that's twice differentiable in this edge space, Laplacian of it could blow up like r to the minus 2, which is obviously not what we want. And it's exactly for this reason that we restrict to this domain, this Holder Friedrichs domain. So this d0 alpha corresponds to the set of twice edge differentiable things whose Laplacian is still bounded. Okay, so somehow the problem is then to determine what is the actual extra conditions which characterize these Holder Friedrichs domains. And the answer is the following, that any element of this Holder Friedrichs domain has a partial asymptotic expansion. So it looks like a sum of terms where I have possibly a log term times a coefficient, a leading term, an r to the 1 over beta term with very particular theta dependence, and then some remainder term which vanishes like r squared. Okay? And now as I say down here, one of the hard things about taking this approach, if you try to follow it too carefully, is precisely the fact that it's very hard to characterize the regularity of these coefficients. You can do it, but it adds a lot of extra complications to the problem. That was something that hung me up for a long time. The funny exponents that arise here, so in particular this 1 on beta, are the indicial roots of this problem. And the solutions that we're interested in are the bounded solutions. That corresponds to taking the Friedrichs domain. Okay, so I'm omitting the log coefficient. Okay? And one other big difference that distinguishes the case where beta is less than 1/2 from beta greater than 1/2. So when beta is less than 1/2, this term is irrelevant because that's sort of absorbed into the junk term. Okay. Okay, so what Donaldson pointed out was something simple and yet extremely important in this, which is that if you look at the Green's function for the Laplacian, so you take the Laplacian associated to one of these edge metrics, you look at its Green's function, which you may know exists by the sort of general arguments, you'd like to see what happens when you differentiate it once or twice. So I call these sort of, Riesz-type potentials. So you take the, it's like the Newtonian potential differentiated once or twice. If you do that with real derivatives, you can see right away that you'll get into trouble. And what Donaldson observed was that if you do it with complex derivatives, even these sort of stronger wedge derivatives, you're still okay. So somehow the complex derivatives, there's only certain combinations that arise. You don't have every possible real second derivative, in particular in this thing. And it turns out that these Riesz-type potential operators are still bounded on these Holder spaces. And so based on this is what allowed Brendel to sort of carry out the whole Aubin-Yau-type proof when the betas were less than 1/2. So one of the key points in our theory was the following, that in fact, if we take these complex derivatives composed with G, then in fact, in all cases, you're actually able to understand all of these real derivatives. So when beta is less than 1/2, you're able to get all of these real derivatives, and when beta is less than 1, you're able to get these particular complex derivatives. And this is distinguished from what Donaldson had done, who in some sense had realized the impact of this type of result. But in particular, we're proving these on these weaker types of edge spaces. Okay, so that was, I think, one of the, this was sort of the key linear result in our paper. And now passing on to the nonlinear aspects, the a priori estimates, let me just say some words. So again, we haven't seen sort of how the asymptotics are. I stated what the asymptotic expansions of solutions look like, but we haven't seen how they played such an important role, and let me try to do that now. So as I said several minutes ago, one tries to obtain a priori bounds on the C0 norm of sequence of solutions, the C2 norms and C2 alpha or C3 norms. And the C0 estimates are, following what Yau had introduced, one needs some sort of Moser iteration argument, which you have to show works in this context, but you're able to get a sup norm bounds. The C2 estimate is what breaks down quite radically. So it turns out that because we don't have a lower bound on these bisectional curvatures, we had to develop a completely new approach. And it turns out that there is an old inequality due to Chern and Liu from the late 60s, I believe, which was a type of generalized Schwartz lemma. And it turns out that if you think about it in the right way, it actually gives you a C2 estimate. Well, it's giving you a sup norm for the Laplacian, which is roughly speaking a C2 estimate, which is all you need here. And remarkably, it only uses an upper bound on the bisectional curvatures. Okay? So that was kind of a great piece of luck that this inequality was sitting out there, and we had to absorb it into this. And the other part of this that I had mentioned was that in this continuity path, sorry, that should be S times omega sub S here. In this continuity path, the solution has Ricci curvature, which is automatically, just by the definition of the equation, has Ricci curvature, which is bounded below. So again, I'm not going to say too much about the details about that, but one still needs to check that this initial metric does have an upper bound in its bisectional curvature. So as I said, there's no lower bound. You can definitely compute that, and it just definitely fails. There's no ifs, ands, or buts about it. And there was a remarkable calculation done by Chi Li, a student of Tian, and which he and Rubinstein carried out in the smooth case, in which Yanir and I carried out in this simple normal crossing case, which is, a very long calculation. I wish I had sort of an intuition about why it works, but it does, and which shows that the bisectional curvatures are in fact bounded above for this model metric that we wrote down, this, omega plus epsilon times the sum of the dd bar of mod si's to the 2 beta I. That has bisectional curvatures bounded above for all cone angles less than 1. Okay, so finally, here's the last point, and this is sort of the interesting one in terms of asymptotics. So if you'd like to prove higher order estimates, now let me say a few, so let me say a few things about this. So in the compact smooth case, one can either prove, as Yau originally did, or Aubin originally did, prove C3 a priori estimates, or you can prove what turned out to be sort of a more powerful, general PD technique due to Evans and Krylov. You can prove C2 alpha estimates. Now, our solutions, remember I wrote down this asymptotic expansion, so let me write this down. A0 plus r to the 1 on beta times A10 sine theta plus A11 cosine theta plus, now if I write down the full expansion, which I do in a few moments here, r squared times A20, and then there's going to be a bunch of other terms. I'm going to have a term here which is going to look like r to the 2 plus 1 over beta, for example, and many other terms like this. And in particular, when beta is between 1/2 and 1, this r to the 2 plus 1 over beta is strictly between 2 and 3, and you have no chance at all of proving in the wedge spaces, in the traditional d by dr derivatives, a C3 estimate. It just, 3 derivatives gives you a singular function. There's no chance of getting an estimate for that. So in fact, what we do is look at these scale invariant spaces, these spaces where I differentiate with respect to these degenerating vector fields, r d by dr and r d by dy, and look at how those derivatives are estimated in small Whitney cubes. So I just take a cube of size epsilon at distance epsilon away from the divisor. Okay? And it turns out that the whole problem is kind of roughly scale invariant, approximately scale invariant, and in the edge spaces, which are completely scale invariant spaces, one can just sort of dilate up. So here's this, here's the singular set here. Here's the divisor. I take a very small cube here. I dilate it up to sort of a unit size cube and apply the standard Evans-Krylov C2 alpha estimates and dilate it back down, and I get my C2 alpha estimate sort of for free, just appealing to the interior case. Now, there's a catch with this, which is that so let me see what I want to say here. The catch is that one is able to, one then has a priori bounds in these C2 alpha edge spaces, but the problem is that if you use the continuity method, you get a limit of solutions using these a priori estimates, but it has very weak regularity along this edge. So in other words, what I've done is I've taken the continuity path, but if I want to show that the solution which exists for s less than some s naught, if I want to extend that to equal s naught, if I want to get a solution at s equals s naught, I can do so, but the expense I pay, the price I pay, is that I get a very badly behaved solution there. These edge spaces have very weak tangential regularity along the edge. Okay, so in fact, one needs to know that any solution of one of these complex Monge-Ampere equations automatically is smooth. Well, smooth in this context means has an asymptotic expansion that looks like this. And I've missed a closed parentheses. It's supposed to encompass both these things. So this r to the I on beta plus L is supposed to encompass both the cosine and the sine terms here. Okay, so this is what the full regularity of solutions looks like. There are some exceptional cases where beta is rational and you might get log terms high up in the expansion, but this is what the actual regularity of solutions look like. And so this is sort of the way out of this impasse, and this is sort of a theorem that sort of has many antecedents going back, that solutions of these degenerate linear and nonlinear equations have good tangential regularity a priori. So in some sense, the point is that we were able to bypass any subtleties that came up in sort of the other approach to this problem using the wedge spaces. Namely, we were able to circumvent all of that by looking at these scaling arguments and just appeal to standard interior estimates. So this step just takes half a page to write down. This is a very simple argument. But then the price you pay is that you have a hard regularity theorem to prove. Okay, so that is the point I wanted to make, is that this regularity theorem serves as a crucial intermediary. So it's not just sort of a nice thing to say, well, solutions just happen to be smooth at the end of the day. In fact, it's really crucial for allowing the cycle to close, going from the closedness back to the openness argument. Okay. And it turns out that in sort of the more detailed investigations of the geometry of these metrics, understanding the form of this expansion and working with it very carefully turns out to be really crucial. So something that's turned out to be very important in sort of some of the compactness terms is understanding when D is totally geodesic, by which I mean if you have a geodesic which starts away from the divisor, can it somehow adhere to the divisor? Or can it sort of bounce off? Do shortest geodesics cross the divisor? And it turns out that at least when the cone angle is small enough, there's some sort of funny cutoff at 2/3, some other funny cutoff at 2/3, D is totally geodesic in the sense that you can't have that behavior for minimizing geodesics. If you have a minimizing geodesic between 2 points that are not on D, then it doesn't touch D. Okay? It's probably true for all beta less than 1, but we don't have a proof of that fully yet. And then a few words here I want to say about simple normal crossings. So it turns out that the analysis needed is substantially more difficult, and the regularity theorem looks much more involved, so I didn't want to state it in this sort of generality. The techniques one applies are of geometric microlocal analysis, namely one has to blow up M along each of the divisors. So this funny symbol says I take a real blow up of M along this union of divisors, and because of the transversality, I can do this in any order I want. It's a manifold with corners. There's a sort of a nice full coordinate system, if you like. The theta is the angles. The r's are the real radial variables coming away from the hypersurfaces created by this. So in the codimension, in the case of a simple normal divisor, what this corresponds is to replacing the divisor by sort of the tubular neighborhood. So in other words, the blown up manifold just looks like the exterior of sort of a tube around that divisor. Okay, so I've replaced this codimension 2 boundary by a codimension 1 boundary. And then, well, that's sort of a technical artifice, but it allows you to sort of separate out the various types of behavior that as you approach the divisor. And this is all the more important when you can approach from many different directions, when you have all of these RJs. Okay? So the brief comment I wanted to make here is that the solutions are not polyhomogeneous, so I don't have a regularity theorem that's quite as simple as this, where I just have several R variables. And it turns out that one actually needs to blow up the intersections of the R equals 0 coordinates. So that, I might have, just to again say very roughly what might happen, the right regularity statement says that let's suppose that here's R1 and R2. R1 corresponds to approaching divisor 1. R2 corresponds to approaching divisor 2. It turns out that the solutions are not regular or smooth or polyhomogeneous, and these coordinates, actually you have to blow up that corner there. So they're smooth in sort of polar coordinates in R1 and R2. So that's just the regularity that's associated to the problem, and you have to deal with that, and it enters into all of the calculations that one deals with, both the linear analysis calculations, but even the geometric calculations about the boundedness of the bisectional curvature. Okay, so this was a review of sort of a number of developments in this field of Kähler-Einstein metrics, where these asymptotics played sort of this, what I found a very surprising role, and actually the nonlinear aspects of the problem depended very crucially on this linear regularity theorem, which ordinarily you wouldn't think would happen. So I will only get to the second of my 3 topics, and what I want to talk about for the remainder of this talk is something that's rather different, though you'll see the geometry is quite analogous in some sense. So I want to look at a very classical object, the Riemann moduli space, all conformal structures on a given compact surface. I fixed the genus to be gamma greater than or equal to 2. And so I'm modding out by all diffeomorphisms versus modding out by diffeomorphisms which are isotopic to the identity, which is the Teichmüller space. And so I'm interested in the moduli space in particular, Riemann moduli space, R sub gamma. Okay, which is well known. This is isomorphic to a ball of dimension 6 gamma minus 6. And this picture is kind of like taking the quotient of hyperbolic space by a discrete group, where the group gamma is replaced by this very interesting object, the mapping class group. Okay, so this is a subject of enormous interest and study, comes up all over the place. Now, this object, R sub gamma, is a rather singular object. Well, it has singularities that come from the group quotients, and I'm going to regard these as trivial. So they're finite orbifold singularities that appear in sort of the interior of moduli space, and I'm going to regard them as easy to deal with because, in fact, you can just pass locally to a finite cover. So for all the problems that I'm interested in, these interior orbifold singularities are irrelevant. So I'm just going to pretend that R sub gamma is smooth in its interior. Okay? On the other hand, the thing that's, well, before I talk about its compactification, let me tell you about the Weil-Petersson metric, which is one of the many natural metrics on T gamma, but a very classical object. So here's the definition, that if I have two elements of the tangent space, and I'll say a little bit more which realization of the tangent space I'm talking about, then I define the Weil-Petersson inner product of kappa 1 and kappa 2 by taking the inner product of those symmetric two tensors, regarded as two tensors on the surface sigma, with respect to the hyperbolic metric corresponding to that point on the moduli space, and I integrate it over the compact surface with respect to the area form. Okay, so it's a bit of a meta object because these kappas are tensors, symmetric two tensors, or holomorphic quadratic differentials, depending on your preferences, on the surface sigma, but I'm thinking of them as tangent vectors to the Teichmuller space. And here's how you get a number out of them. Here's how you take the inner product. Okay, so it's the canonical L2 pairing. So this is not a complete metric, even on this Teichmuller space, so there are rays that go out to infinity in this Euclidean space which have finite length with respect to this metric. This Weil-Petersson metric is invariant under the mapping class group, and hence we can think about it as a metric on Riemann moduli space itself. And it turns out that that object now, moduli space with the Weil-Petersson metric, has finite diameter. Okay? So we can compactify it in the normal metric way, corresponding to this Weil-Petersson metric, and I get some compact singular space. And the remarkable fact is that this is identified with sort of a very classical object, the Deligne-Mumford compactification, which is an algebraic geometric object. Okay, so that's fortunate because understanding the metric compactification of even a very nice metric like this is often a very hard task. If you just take a metric with some sort of open manifold even with a nice metric of special geometry, understanding what the asymptotics of the metric look like in infinity and what are the points you have to add on and what's the structure of this stratum in infinity, that can be an extremely challenging task. And fortunately, this is sort of subsumed by this identification. Okay? So, in fact, using this Deligne-Mumford picture, the singular set, namely the points at infinity, the points that you add on via this metric compactification, and again, I'm neglecting the orbifold points, so I'm lying slightly, is a union of immersed divisors. Okay, so this looks a little bit like the picture I talked about before. I have roughly speaking, some sort of complex space, and there's sort of a bunch of immersed divisors which have simple normal crossings inside it. Okay? These divisors actually correspond to something, so this is all a review of material much better known to many of you than I am sure. These divisors all have a very simple geometric description, which is that I take my surface, so let me draw the standard picture here. I take my surface and divide it up into pairs of pants by simple closed curves. So let's say here is sigma, genus 2 for simplicity, and I can divide this up into simple closed curves like this. Divide it up into pairs of pants, so I take a maximal collection of disjoint simple closed curves, and I can take a fixed hyperbolic metric that represents an element of the Riemann moduli space by definition, and I can take the geodesic, which is homotopic to that curve, and take its length. So that defines these length functions as functions on this moduli space, or at least on Teichmuller space. And it's known that sort of the only way that you're going to degenerate to infinity is if some of these length functions degenerate. So in other words, this collection of simple closed curves is a topological object, which I've fixed a priori, and their lengths with respect to the corresponding hyperbolic metrics, if they stay bounded away from 0, then I'm staying within a compact subset of the moduli space. So, said differently, again, the divisors have to somehow correspond to the lengths going to 0. Okay, and in fact, the divisor dj corresponds to the lengths of one particular one of these curves going to 0. Okay? So, and there's a subtlety that these divisors are immersed rather than embedded, so that comes from the fact that, for example, under the mapping class group, certain curves can be identified with one another. Okay? So, so the limits of these sequences of hyperbolic metrics are going to correspond to, so for example, the prototypical picture, and I'll keep this up here because I'll refer back to it, is that in the limit, as the length of that curve has gone to 0, but let's say the other curves here are staying bounded away from 0, so if this length tends to 0, the limit is going to be a hyperbolic metric with two ends, both of which are cusps, so you have a finite area surface. Okay? And sort of conversely, you can take a surface with two cusp ends like this. You can open up the cusps a little bit. You can, if you like, take a hyperbolic metric which doesn't come down to a cusp, but comes down to a geodesic, which is very far off, and you can attach these two pieces together along the geodesic to get a hyperbolic metric with a very long neck region surrounding that geodesic. Okay, so that's what the surfaces, the hyperbolic metrics, look like very near the divisor. So in other words, the limiting objects are these complete finite area hyperbolic metrics. And there's one extra parameter here, the rotation parameter, which corresponds to when I attach along the geodesic, I can do it with a twist. Okay, so here's what the Weil-Petersen metric looks like in these coordinates. So along a simple divisor, along a divisor corresponding to just one curve going to 0, one has this funny form, dl squared over L plus L cubed d theta squared plus dy squared. Okay, now again, I'm sort of neglecting all higher order terms, which are a very interesting and important part of the story, which I'll be trying to describe a little bit as I go along here. And I'm leaving off constants. There's like a, I don't know, pi squared over 6, or, I forget what the constants are in front of these two terms, but they were known explicitly. Okay? So this is a rather degenerate-looking object. I'll write this in a slightly more familiar form later on. So the rough quasi-isometric form, namely that the Weil-Petersen metric was bounded above and below by multiples of this, was understood by Howie Mazur in the 70s, and there was much more refined work by Scott Wolpert in the mid-late 90s, and Sumio Yamada had sort of the most precise form of this metric. And he had sort of the leading terms of this metric and a couple of terms in the expansion, but not too many. And in fact, probably the most extensive calculations that had been done were a series of papers by Kefeng Liu, Xiaofeng Sun, and S.T. Yao, where they were interested in not the Weil-Petersen metric, but this sort of interesting cognate called the Ricci metric, which comes about from the remarkable fact that if you take the Weil-Petersen metric, you take its Ricci curvature, that turns out to be negative definite. And so its negative forms a metric, which is an interesting metric itself on moduli space. And so they were interested in understanding that metric and some of its geometric properties. So in particular, if you want to understand the curvature of the Ricci metric, that really corresponds to taking 4 derivatives of the Weil-Petersen metric itself. So, there's pages and pages and pages of calculations there. It's very complicated. But that's as far as people have gotten. So they've gotten 3 or 4 terms in the expansion. So for the geometric purposes that they were all interested in, that sufficed. Now, just to point out, when you have when you're at a crossing of divisors, then you're going to have several length functions and the corresponding twist functions, and the Weil-Petersen metric has this sort of product form. And the important thing is that it really does look like, to leading order at least, it looks like just a sum. It looks like an orthogonal sum. So what that corresponds to is the very nice geometric fact that if I were to pinch 2 geodesics simultaneously, so this one and this one, then I'd be developing a very long hyperbolic neck here, a very long hyperbolic neck near this one, and they're very far apart. So when I take this Weil-Petersen inner product, they see each other, but sort of only in very high order terms. Okay, so there really is some sort of orthogonality between these divisors to leading order. So this is what I say down here. And so finally, here's the form that I want to write, and of course I have a typo there, unfortunately. So I introduce the square root of Lj as a new polar coordinate, Rj, and then the Weil-Petersen metric looks like drj squared plus rj to the 6th power times d theta j squared. So sorry, I forgot the d theta j squared, plus the metric along the divisor. So now you can see sort of the analogy with the Kähler-Einstein picture I talked about before. So I have this picture where I have a series of divisors which have simple normal crossings, and I have a metric which is rather singular in the transverse directions. So the metric is no longer a cone in the transverse directions, but it actually looks like a cusp. Okay? So I call this sort of crossing cusp edges, for lack of a better name. Got to think of a better name for that. And it's sort of fairly horrible geometrically. I mean, there's unbounded sectional curvatures, and it's a very degenerate object. Okay, so the first theorem I want to talk about today is the fact that the Weil-Petersson metric, so as I said, there was all this work I mentioned back here of understanding the first few terms of an expansion. So in fact, there's a complete asymptotic expansion. So the Weil-Petersson metric is completely regular at the divisors. So you say, well, the exponents are integers. That means it's sort of smooth in these r coordinates. But there might be log terms, and in fact, there might be some funny spurious terms. I haven't tracked down all the possibilities. So let me just sort of hedge my bet and just say there's a complete polyhomogeneous expansion. And something of interest is to understand what the coefficients of these various terms in the metric are. And so in principle, we can compute them, but in practice, it takes pages and pages and pages of calculations, which has never been my forte. So, but we hope to be able to do that sooner or later. So I want to say a few words about the proof and some applications of this. So in the next couple of slides, I just want to give you some ideas about what we want to do with this and then how we actually prove this theorem itself. So one thing I wanted to mention right away is that we don't use the complex analytic picture of thinking of the tangent space consisting of holomorphic quadratic differentials, but instead talking about using a more global analysis point of view, thinking of it as transverse traceless tensors and using real operators instead of complex operators. That's not too important. It could probably be done either way. But in terms of proving a regularity theorem like this, this is very different than the previous Kähler-Einstein theorem I told you, because this metric doesn't a priori satisfy an equation, right? So it's a nice canonical metric, but it's not a solution of a PDE. So one needs to approach this problem in a different way. There are PDEs that are used to prove this to understand this expansion, and what the PDEs are in fact, essentially the Hodge Laplacian on this degenerating family of Riemann surfaces that one needs to study carefully. Okay, so before describing the proof, let me tell you about a few applications. So this was the thing which I'd mentioned at the beginning of the talk. So suppose that we look at the Laplacian on functions for the Weil-Petersson metric on the singular space. We look at Riemann moduli space with the Weil-Petersson metric and the scalar Laplacian. And the first question you can ask, because this is an incomplete space, is, does it make sense to think of this as a self-adjoint operator, or what are the self-adjoint realizations? And our theorem is that, in fact, there are no choices to be made. It's essentially self-adjoint, okay? Which is not an obvious theorem, because anytime, even with conical singularities, that there's something real to be done there. This kind of theorem for manifolds with sort of these edge-type singularities was, in fact, done by Cheeger in the early 80s. And so this is extending this, in a sense, to sort of these more singular types of metrics. This Laplacian has discrete spectrum, and it satisfies a Weil law. And so here are some things that one has. So in particular, the Weil law is standard. So in fact, you just get the dimensional constant times the volume times lambda to the dimension over 2. Okay? So what that's really saying is that the spectral contribution of what's happening near the cusps is, near these divisors is negligible. It's low order. Okay? This isn't sort of so shocking given sort of the great advances in spectral asymptotics by Ivry in particular, that you expect these sort of cusp-like terms to create sort of strange effects maybe in the secondary level, but not at the top level. But indeed, that's what we see. However, here's something that uses the full strength of the asymptotic expansion that we use. So in fact, you can look at the heat kernel of the Weil-Petersson Laplacian on moduli space, and you can ask, is there an expansion of that as t goes to 0? So if one's trying to understand spectral asymptotics, this is extremely important. And, well, if you're trying to understand various global spectral invariants, and it turns out that it does have a complete expansion as t goes to 0. This is recent work of Jesse Gell-Redman, a student of mine, former student. And this really needs sort of the full expansion of the Weil-Petersson metric. So if you don't have the expansion, suppose you just know the first few terms of the Weil-Petersson metric near the divisor, you will get some sort of rough bounds on the trace of the heat kernel, but you certainly don't get a full expansion. And in particular, if you're interested in more subtle things like understanding the t to the 0 term in the expansion. Well, it's a very high-dimensional object, and if you want to take the expansion of the heat kernel all the way up to t to the 0, you better have a lot of regularity of the Weyl-Petersen-Laplacian, or of the metric. So this was really our motivation for understanding the asymptotics of the Weyl-Petersen metric. And the minute you understand the heat kernel to this extent, then you can talk about the determinant. And so right now what we know is that there is a determinant. You can make sense of it, which is a non-trivial fact. What it means and some identities involving it, I mean, we have some ideas, but so far that's still work to be done. And let me just mention a few things that should be done and which we're, to some extent, working on. One is to understand the Hodge-Laplacian for higher degree forms. Does one have obstructions to essential self-adjointness for these? And again, you expect to involve at least some of the higher asymptotics in those cases. The Gauss-Bonnet theorem was understanding what the Euler characteristic is of moduli space in terms of the Weyl-Petersen metric. This was subject of some very nice work by Liu Sun and Yao about a decade ago. And they left as an open problem, a very interesting one, is there a signature theorem on this space? And I think that's probably our main goal in this business, is to try to understand if there is one. Okay? So I'll finish up in just a moment. Let me just sort of point out that to prove essential self-adjointness, one can sort of take various approaches, but ultimately what one would like to do is to understand that if you have a function u such that you just know that u is an L2 and its Laplacian is an L2, you'd like to say that u has a little bit of extra decay. This is really sort of the main function theoretic input that you need to have. It's sort of a PDE regularity fact that any element of the maximal domain decays at a slightly, some fixed a priori rate. And so in fact, what you do is you look at a weight function times u, and you get estimates for this L2 norm using a complicated chain of inequalities, which the centerpiece of which is a Hardy inequality with a precise constant. Okay. And so one thing that comes out in this proof is that it's very borderline. Remember, I had dr squared plus r to the 6th d theta squared. When k is bigger than 3, if I have a power bigger than 6 there, this turns out to be a much easier estimate. And when k is equal to 3, it's still true, but it's harder. So, okay, well, I think in the interest of time, I'll finish here and leave it at that. Thank you very much.